Hello, in this video we're going to look at the process for creating a simulation using ROS and Gazebo to simulate a robot featuring closed kinematic chains. Because of the ease of use, we will use the SOLIDWORKS URDF plugin to export the open kinematic chain structure of the robot, then take this information from the CAD to create an STF, which will be capable of simulating these closed kinematic chains. Although if you understand the concepts presented, it is possible to create a STF directly without using this plugin. Regardless of your approach, you are going to need to have a description of your robot, link geometries, and joint locations. CAD packages offer a convenient way to get all of these. The use of closed kinematic chains is fundamental in machine design, providing the basis for numerous mechanisms. Having a procedural approach for including these in simulation is important because mechanisms provide the robot with the ability to perform tasks. The simulation and SOLIDWORKS parts files are included in our GitHub repository. Secondary discussions presented in this video will cover some of the relevant topics such as methods for creating simulated test environments, texturing, and conducting a simulation, and experiment with your simulation. So before going into our model, let's look at the system. So we see here that we have this closed kinematic chain here, which serves as a basis for our locomotion system, allowing the robot to traverse chaotic terrain. So from here, we have two parallel closed kinematic chains up front, which constitute the longitudinal bogies. In the rear, we have a transverse bogie, which is an open chain. So here we have the longitudinal bogie, the closed chain. So we go from our base link to our bottom link to the middle two vertical links here and here, the front wheel, middle wheel, that's where it ends. So if we were going to do an export as an open chain, we want to double back from this top link, which returns to the base link. As opposed to this, we can look at the rear transverse bogie, which goes base link to transverse bogie to each of the wheels. As you can see, it doesn't double back onto itself. So for our export process, we're going to try to make this closed kinematic loop an open kinematic loop, and then add the joints later. So we can either do this by going from the bottom link to the wheels, or from the top link down to the wheels. It doesn't really matter in this case. So for this example, we're looking at simulating the locomotion configuration of the robot. So to do this, we have stripped down the extraneous parts from the assembly that we would not need, such as the upper assembly and the grousers that you saw on the wheels that provided traction. The grousers, so in this export, we're going to create the collision model. So these grousers that in actuality help increase traction can't be used in simulation because Gazebo uses rigid bodies. The next thing of note is that we repositioned our assembly such that the origin is in a logical place. Now this is important because the origin is going to dictate the moment of inertia of the central chassis or the base link. With your system positioned correctly and it is simplified to the point where you want to simulate it, the next thing to do is to think about restructuring your mates. So you want to structure your mates in a fashion that makes sense to the kinematic structure of the robot, because the URDF exporter is going to try to read in your assembly to make sense to see where the joint axes and origins are going to be. So you might completely delete all the mates of the assembly that you're working on for design purposes and create a whole new set of mates for your simulation assembly. The other thing to think about is because we're exporting a URDF, which is a tree structure, we're going to export it in a way that's going to be a series of open chains. So keep that in mind as well as you're creating these mates. So now our assembly is ready for export. So we'll go up, and assuming you have the SOLIDWORKS to URDF plugin, we can go to export as URDF. Now I pre-prepped this export, though when you're doing it yourself, it's a good idea to build it piece by piece by piece. For instance, you go from the base link to one of these right top links and then work your way down and see if the accesses that you create, see if the joint locations are correct and everything is coming out correctly. So in this export, we have the base link, which represents the central chassis of the robot. It has 5 children. So the URDF is structured as parent links and child links. So this base link is the central parent link, and from that all other links branch out, like the tree structure we mentioned earlier. So direct children from the base link include the right top link, the right bot link, and left top link, left bot link, and the transverse bogey, which we named the rear rocker link. So when setting up your structure here, you're going to name your links. It's nice to name it in some logical structures so that when you're going back and looking at the URDF or working on the URDF, you can kind of see what these links are, what they represent. So also to remember to use underlines or underscores instead of spaces, because spaces will cause problems. So the reference coordinate system and the reference axis usually should be set to automatically generate. I haven't found great success with forcing an axis or a coordinate system in, so it's best to try to make your assembly fit how it should be so that these coordinate systems and axes will automatically generate. The thing that you do want to specify is the joint type. So if you don't do this, sometimes it'll do it as fixed when you want continuous, or if you want prismatic, it might switch to fixed. So this forces it to apply the correct degree of freedom that you want for the joints. So here we select a body that represents the link, the top link, and we say it's a child of the bottom link. So now we're going to start to construct our series of open chains. This is a closed kinematic chain that we're hoping to simulate in the end. So we'll go from the top to the right vertical back link. It's a vertical link in the back. And then to the middle, right middle wheel. You can see they're similarly named and the joint types have been set. Again, here we have a similar thing where we're building the tree structure downwards. And then we complete the series of open chains with the bottom link. Now, one thing that I sometimes find helpful in troubleshooting, because it can get somewhat tricky to get an export correctly, is sometimes it's hard to find these axes, so you can actually group multiple bodies into a link. So you see this vertical linkage includes an axle. Sometimes I include axles. I found that sometimes it helps the exporter go through, though that's purely anecdotal. So then you would continue building these tree structures on the other side, working it such that the axes and orientation and origins are where you'd expect them to be, working it down to the other side until you come to the rear rocker. Similarly, you would set this, you give your link name description, your joint name description, specify the joint type, and then finish the chain there. So with this done, we can preview and export now. So this is going to create the URDF model. So we can see it creating the origin at our origin. That's the global origin, and it's creating this URDF reference. So now we see it that it's correctly found the origin and axis for this top link joint. Now, one thing to remember is that the origin, that the revolute joint or continuous joint, as described by URDF, eliminates all but 1 degree of freedom. So the origin can be any point on this axis, and it still effectively eliminates all the degrees of freedom except for the rotation about that axis. So if the origin comes in a place that you might slightly not expect, That's not necessarily something that you need to worry about too much because it's completely acceptable. So when you're doing this, you can kind of watch your assembly here to see if something gets fixed. If you see something gets fixed, that's usually a sign that the assembly can't solve the URDF structure with your given as you've currently constructed your assembly. So here we see it's constructing the origins and axes for the joints, and it's all the way to the left side now. It's completed the series of open chains on the right side, so we go from the top all the way down to the wheel, and then the bottom. And now it's done a similar thing on the left. So for the base link, the inertia is going to be based on its origin. But for these links, the inertias are going to be based on the axis of rotation and the part geometry. And that will be given directly from the CAD, which is one of the reasons that makes it quite valuable. So now we're at the rear transverse bogey. And it's finished its export process. So one thing that you can do before even looking at this tab here is to look at all the joints and axes, origins and axes it's created to see if they make sense. Now this looks like kind of somewhat of a mess, but you can kind of look through it to see if they are where you would expect them to be. Alright, so now we have our export has gone through successfully, and we can look at the joint properties and just kind of investigate to see whether these are what we would expect. So we see the axis of rotation here for the continuous joint, and then the position and orientation of the origin. Now we use URDF uses scientific notation. So if you get something like this, we see e to the negative 17. That's essentially 0, and you don't need to worry about that too much. You can switch it to 0, or you can leave it. As you can see, this is radians rounded. The next tab is link properties, so you can examine the link properties. And we see it's exported the moments of inertia, as well as the origin and the mass in kilograms. Now if you strip something down, you might want to go back here and manually correct the mass to what the initial mass was because you've simplified it. That's an option that you can take. So now we can hit finish and then save. We'll call it example 1 or example closed. So it's now saved on the desktop. Let's take some time to look at the contents of the export before we try to implement it in Gazebo. The two important things to look at are the robots folder and the meshes folder. The robots folder contains the exported URDF. Now this is interesting to look at because you can somewhat check again to make sure everything was created correctly, and also we can look at how one might create a URDF without using the exporter. As you can see, it can become a significantly tedious process, which is why I personally like the exporter. But if you were to create a URDF or SDF on your own, you would use this structure. This is the URDF structure. If you had the SDF structure, you create the SDF structure, and you'd input these values as shown. The documentation on how to create a SDF or URDF is pretty strong, and the meshes that you'd use here you can include. So if you wanted to create a mesh using a different package and put your own link and joint descriptions. That is something that's possible, though it can become somewhat of a handful. So for instance, we see our visual mesh and our collision mesh, along with the moment of inertia of the link. And then we can see some joints later on. The next thing to look at is the meshes. Now sometimes the meshes can come out crooked at a weird orientation, and we just want to make sure that the meshes are what we expect them to be. So I opened up a few STL files for you here, which you can check out. So here we see our wheel. The STL is one solid graphics, so that came out as expected. And the bot link, so again, as the STL file. So because they're created as STLs, STL is a very common file format. They can be opened in most CAD packages or 3D packages such as Autodesk or Blender. If you want to apply additional texturing, for instance, to create a visual mesh over your collision mesh, you would open up this STL in the 3D package that of your choice, and then you can edit it in there, applying maps or coloration as you might please. Let's look at an example of that. So here we have a wheel that we textured. To do this, we want to include the grousers just for aesthetics. So we did the similar export process, except the grousers were not suppressed, and this created that STL in the same orientation as the previous export. And we took that STL and textured it. As we can see, we applied a small bitmap to this face. Then this part can be exported as a Collada file. Be sure to include the image in your Collada file. So we can export as Collada, and then we have our DAE and the associated image, and then we can include that in the visual mesh description.
We should have our export from SolidWorks. It should be in a zip file, and if you download it or switch it over from the computer that you were using SolidWorks on, you should be able to see that the file is right here. So the sudo sim.zip, if you're following along with the tutorial, that is. So now in our
be created similar to how you create a robot. Though environment items are usually simpler because they don't have to perform tasks, so the primary focus is going to be geometry and texturing. Either description format can be used, although STF might be advantageous in some scenarios because it offers more features such as lighting. In the beginning of creating an environment, consider what important elements are essential for the simulation and how a simulation can encompass these within its constraints. So the system, the environment that we're trying to create is a chaotic terrain for the NASA robotic mining competition. So a good way to start would be to look at the available information on this. So we can look, so here we have a general dimensional layout of the arena, which can be used to build a simulated arena. This is the first important piece of information. The next important piece of information is going to be the terrain elevation deviations. So we can see here by scrolling through that the arena is going to change by plus or minus 30 centimeters. So in our simulated environment, we're going to want to encompass this feature in our environment. So you can make these meshes for the geometry in any way through any software that you feel most comfortable with. In our case, we made it with SolidWorks using the Freeform tool to model the terrain elevations, which can be seen here. And then we exported it using SolidWorks to URDF export because of the ease of use, and then took the STLs created and made a DAE to apply some texture with which we'll show here. So simulation is always going to be a simplification of the real scenario. One always must be cognizant of these simplifications, and where the results of a simulation can be applicable and where they might not be accurate. With our simplifications, we can say a few things. For instance, we can look into relevant research on mobile robotics. For example, in analytical configurations for wheeled robotic locomotion, it is stated that a well-designed locomotion system smooths the motion of sensors and accommodates the deployment of tools. And other work states the ability to equilibrate the normal force throughout the wheels contributes to an effective configuration. So these are some of the characteristics that we can investigate within the confines of our simulation with this creative environment.
Home folder, we were going to want to actually make the folders for our Catkin workspace, so I'm just going to make a new folder, call it ROS, and then have the SRC folder. I'm just going to use ROS, the name ROS, instead of Catkin_workspace for now, and then we'll create this, and we will go into this ROS SRC folder, and what we will do is we will copy the Sudus sim zip file into this folder here. And we will unzip it, and now we can just simply remove the zip file. So now that we have the contents inside the zip file, we see that there's a launch folder, meshes folder, robots folder, and a textures. Pretty much the textures folder and this manifest XML can actually be deleted, but you can leave the textures just in case you want to be able to use the folder later and place things in there. So the manifest XML you can get rid of because that was used in older versions of ROS, and this plugin is actually has not been updated in actually a good amount of time. So we are not going to use this file anymore. If you go into the robots folder, you'll see that the URDF file from the exporter is here, and if you open it up, these are going to be all the contents for the different linkages, the different joints, and inertia parameters, mass values, and etc. So now what we want to do, as we explained earlier, is that the 5-bar linkage is going to be a graph-like structure. We're going to need to turn this URDF file into an SDF format. So the way that we do that is we do gzsdf print the file, the URDF file, and then we want to output the name of our SDF. So you can have it the same name, just a different file extension. So now you should see that the .sdf version of the file is going to be there. So now you want to open up the SDF file, and usually what I like to do is in the very beginning I like to insert this XML tag so that everything's kind of color-coded. That's at least when you're using Vim. So I'm just going to copy this from another file that I have, and close it up, open it back, and now everything's kind of color-coded. So I just want to show you one thing. So now that we pretty much have the file in SDF format, what we can do now is we can simply just view how this exported mesh or exported robot is actually going to show up in the current state that it is in Gazebo. So what we will want to do now is we will actually want to copy this entire Sudus sim folder, and we will want to place it into the home folder in the .gazebo models folder. I need to copy. Okay, so now we can go, and this is the by default the .gazebo models folder is actually the the environment variable in the Gazebo resource path, or the Gazebo models path. So this is actually where Gazebo loads all the models that you can insert manually by clicking and placing into the Gazebo world. So actually we will look inside this model config, and actually what this basically does is describe for the for Gazebo what the robot is, who the author is, and what the description is. So here what we want to do is create the name for the robot, the version, the SDF version. So this is actually going to be the same version that's going to be in the SDF. So here you can see that the SDF version is 1.4. This is actually what the GZSDF print command, it outputted and set it into version 1.4. So inside the model.config, now you see version 1.4, and then you specify the path to where the SDF file of your robot's going to be. So in our case, it's going to be in the robots folder and then sudo sim.sdf. So now we are basically ready to just simply open up Gazebo, and then you'll see that the model that we just created into the Gazebo models folder is going to be right here. So if we click on it, you'll see that the model is here in the world. The reason that you don't see the wheels and everything is that the center of the robot is actually right where it should be, and we need to elevate all the components of the robot just probably about 30 centimeters above the current state in which it is. So the nice thing about so this is actually going to fall apart now, since some of the joints are not actually connected during the exporting process. We explained a bit about that. So actually what we can do now is we can just simply delete this. And the nice thing about editing the model this way is that editing the model through using the .gazebo models file path is that you can simply leave Gazebo open and edit the file of your robot on the fly. So now if we go in here and we edit the SDF file, so for example, we don't want it to move once all the components of the model initialize in Gazebo, we can set the static tag to true for the entire model itself. And then if we simply click it here, the model will actually stay in this position no matter what. So now what we will want to do is we actually will want to raise this about 30 centimeters on the z-axis. So here for the entire model, we will want to specify a pose tag, which is going to be an x, y, z of 30 centimeters and a roll pitch yaw offset of 0. So now this previous model is still here, and then now you can see the difference between the two. So now we will just delete both of these. And Gazebo just froze up. Want to insert manually the joints, since we couldn't do it in the URDF exporter. We can actually view the current joints, the placement of the current joints right now by doing view and joints. So basically what this will do is, I can't rotate, show us the location of the joints currently here. So we have a joint in the top corners, and we will want to create joints in the bottom corners here, which we actually left unconnected. So the way that you do this is you actually find the position that intersects between the joint that was created here, joint that was created here, and the intersection between these two linkages here. So just to save time, we here see that this is a manual. I just copy and pasted this from, for example, this joint here that was actually part of the conversion or the export from SolidWorks. I just copied this and I just rewrote the name, the child linkages, the parent linkages, and then just kept pasting it. And then for the joints that we need, so just as a reminder, we need the two bottom joints. So this would be the robot's right linkage, the front vertical link with the bottom link. So on the right of the robot, we have the right bottom front joint, and that's going to be taking care of the joint right here. So we have the child is going to be the right vertical front linkage, which is going to be this one here, and then we have the parent link is going to be this bottom link that's going to be right here. And what we do is we simply copy this process and we just rename, we just have different names for the joints that we need and change accordingly, respectively, the child and parent linkages. So for example, for this right vertical bottom joint as well, right vertical bottom back joint, this one will be taking care of the joint back here. And then the same process is going to happen on the linkage on the other side of the robot, which is going to be right about here. I can't rotate. My mouse for some reason doesn't want to rotate right now. But it's going to be the same process on the other side, where the front bottom joint is going to be created and then the back bottom joint, just like we did here. So I'm just going to take these two joints first. And this is all going to be on the GitHub, so that you can view the joint values specifically. So the pose values, those are actually values from the CAD model. It was also from kind of try and error as to what the actual intersection point is between the two linkages. So here we copy the left joints that we need to specify manually. And now if we want to view the model that we just edited, we still have it as static, so we can actually delete this last one, and we will view this new one, and we'll see that the joints are in the correct locations right here. So we see these arrows, as before. We see an arrow sticking out from this joint here and an arrow sticking out from this joint here, meaning that the joints are in the proper place, and it's going to lock the two linkages together. Okay, so now that we have pretty much all our joints set up on the robot, and the robot actually can stand by itself now, and the closed loop linkage is complete, what we're going to want to do is actually move the pseudosim folder out of the .gazebo models folder, which is right here, and we're going to want to move this folder into back into our the folder that we created for Catkin Workspace. I would probably remove the folder that was there, the pseudosim folder that was here in the Catkin Workspace first, and then copy it over. That way you don't you kind of get a fresh start in the Catkin Workspace. So now that we're here, I already put in the CMake list in the package.xml, so we will just take a brief look into the CMake list. And here what we will do is basically just specify the project name, which is actually going to be the the package, the name of the package here, that's going to be in our Catkin workspace, and then pretty much you kind of just need the rest of this stuff here for just for it to be identified as a Catkin package. We're looking at package.xml here, and here we'll just briefly put in the name for the package itself, the version, just a short description, email, and stuff like that. The dependencies. We don't really have any code too much that needs build dependencies, so this actually doesn't really need to be there. I'm just gonna leave it just anyway. A run depend. So we use robot localization as the Kalman filter node later that I'll talk about, but this is pretty much kind of the only dependency during runtime that we will need. So now that we have pretty much everything in our Catkin workspace, we will want to go back to the root of the Catkin workspace and just type simply catkin make. And once this is done building, like right now, what we're going to want to do is actually edit the bashrc and make sure that our workspace is going to be sourced. So here I'll comment out the other workspace that I had, and below here I will add the path to our Catkin workspace. So it's going to be in the ROS folder that we created. The devel folder is generated as well as the setup.bash script file. We will want to source this, so we want to go back and we're going to want to resource the bashrc file. So now if we type roscd, we should get to our Catkin workspace, which we did. And now what we will want to do is simply go in and launch the gazebo.launch file. And once Gazebo loads the model, you'll see here it's a bit modified version, and I'll explain shortly why, but these are actually the wheels that we made in 3D Studio Max, and these are just for visual purposes here, but you can actually just simply still use the exported model, which is pretty much all kind of white grayish linkage, the color on the linkages here. And so now actually I'll explain. So this is actually also the entire Lunarina that we made as well in SolidWorks, and then we exported here, and we also made basically the textures in 3D Studio Max. So here I'll briefly explain here how this actually works. Is we'll go into the pseudosim folder, and now in the back into the SDF file, we'll go and basically look in. So let me just rerun this real quick. Once this loads, you will see that the base link, base chassis, is actually different than from what it is originally in the export. And actually you'll notice here, if you zoom in, it's a different color. It also has an emblem for NASA. Symbosis is our NASA Robotic Mining Competition robot. You'll notice here that the visual portion for the base link is actually going to have a different file extension rather than having an SDL, which we use for the collision model, the collision portion of the linkage for the base link. It's going to just be the DAE extension, which is actually the exported mesh from 3D Studio Max. So that's going to be just simply for visual purposes. This is actually what goes in the visual tag here. So all you do is place the DAE file into the same path as where you have the STL meshes, or if you place them, organize them into more detailed folders where you have your STLs in one folder and DAEs in another, the collada files, then just make sure that you have the proper path to that DAE file. So now one thing that you also can notice is that the wheels are the same thing. Basically, they've changed. They have a visual mesh on them. So if we kind of scroll down to any part of the wheels, you'll see, so here's the linkage for the left middle wheel, and if you just simply scroll down, you'll see here for the collision model we have the STL, which is actually basically we want to use the STL for the collision model because this is actually going to give us kind of a more precise collision detection model. The best way I can kind of put it, it's a little bit more accurate than the visual mesh, and it's also we want here. So for the visual, we want to specify the DAE, and I actually just used the right wheel, the DAE for the right wheel for all the wheels, and then basically just rotated them as necessary, as they would show up in different orientations when placing them and applying the DAE for the visual mesh for all the wheels. So all you just need to do simply is just apply a rotation, take out the negative sign. It's a bit, kind of playing around. You don't necessarily have to use the right wheel. I did it for simplicity reasons, where I could just copy and paste this and then just take out the negative sign. But it's pretty much just user preference. So now, if you see here, we're not on the ground anymore. We are in the Luna Arena. So the way that this is loaded is if you go into the launch file here, you'll see basically here that the include file for the Gazebo ROS, the launch file for just a simple empty world. One of the arguments is actually a world name, and what that means is basically you pass a value to a .world file that you have created, and what we're doing here is we're passing the world file for the Luna Arena itself. So this is actually the way that you kind of can load a world that you have saved in Gazebo, and basically go off of that in your launch file. And if we can just simply take a glance, the world arena is actually going to be in the repository as well, and I'm going to actually put it into this folder rather than in a separate folder. But I believe if we go into here, you can see that basically this is just a simple SDF file, and what this is basically saying is to include the different models from the Gazebo .gazebo/models folder. So in the .gazebo/models folder, we can actually see here that we have the Luna Arena folder here, and if we actually go inside of the Luna Arena folder, you'll see that there's a lunarena.sdf and as well as a model config. This is actually going to be as well, like I said, it's going to be in the repository, and all you will have to do is basically take the Luna Arena, this entire Luna Arena folder, copy it into the Gazebo models folder, and then it will be there for you to either insert manually or include it in a launch file, for example, like this one here. So that I guess wraps up for the 5-bar closed loop linkage system for the robot here. And if we want to view, for example, well, actually, sorry, it doesn't wrap up. I forgot to mention one thing. Now, if you actually want to interact with the robot using ROS, if we take a look into the let's see, if we take a look actually into the SDF file of the robot, I have it in there. I believe I have it in there already. If not, then we can actually place it. So now, yeah, actually I don't have it in this file. So actually now what we're going to want to do is actually we're going to want to insert a plugin, a ROS plugin, and by doing this, we're going to want to, I'm just going to reference off of one of the previous versions of this model in the past that I've used. All this stuff is actually, it's accessible on the GitHub. You can kind of view the different plugins that I used on my other models as well. But we are interested in the 6-wheel differential drive system. So here, this plugin right here, and this plugin is actually part of a package that you will need. It's called the Hector Gazebo plugins package, and you can either install this by source, or you can install this using apt-get, like this. So either you can do it this way, or you can do it through the source. I think I prefer doing it through the source, as I believe I had a bit of issues in the past with trying to find these plugins, but it's just for basically it's up to user preference. So now that we have this plugin in here, we want to make sure that our joints for the wheels, they are correct. So basically we want to find out what the different wheel joints are going to be, the wheel joint names. So here's the first one, and we can copy this, go to the bottom of the file again. So that was the left mid wheel joint, and I believe this is probably going to be the same name. Yeah, it is. So the joint names are probably going to be the same for all the joints. So we're just going to leave them the same here. Let's just double check this guy here. Yes, it is. Okay. So now we can just simply exit out of this guy here and rerun the Gazebo simulation, and unfortunately you can't leave Gazebo open and insert the model anymore, because you cannot run simply Gazebo standalone and run a ROS plugin without using a ROS launch file and using the Gazebo ROS package and the Gazebo ROS API in order to initialize the plugin. It just won't work. Okay, so we need to make sure. Yeah, Michael, you're gonna have to edit this part here. Let me just figure this out real quick. Process actually named this incorrectly, and I named it just simply mid-wheel joint when it actually should be the right mid-wheel joint. But just for the sake of getting this to work for now, the mid-wheel joint is going to be the joint for the mid-right joint. This, since it's a 6-wheel differential drive plugin, we need to specify both the front, middle, and the rear wheels, the wheel joints. So now we can actually just make sure that the the rear wheels, these are the proper joints, and I do not believe so. So let's just double check what the names are. So rear left and rear right are going to be the names. Okay, so now we should be able to run it correctly with no errors. And doesn't seem like we got any errors here. So what we can do now is, in order to just simply move the robot, we can just run RQT, and RQT actually has a robot steering plugin, which we can just use a scroll bar to simply move or send a command velocity. So here, let me kind of just minimize this. And now if we send a forward command velocity, you'll see that the kinematic loop linkages are going to be moving. They're going to be working in tandem, and then our model is going to be it's going to be working. So there you go.